And the next speaker is Noel Klingler for George Washington University, who will sort of continue the talk by Oleg. And the title of his talk is Deep Chandra Observations of Nebulae Produced by 3 Supersonic Pulsars.
Hi everyone, my name is Noel Klingler. I'm a 5th-year grad student from George Washington University in DC. Can everyone hear me okay? All right. Before I begin, I'd like to thank my advisor Oleg and my collaborators and the conference organizers for this opportunity to present my research. So today I'll be talking about deep Chandra observations of the Nebulae Pulsars and the long extended tails and other features they produce. A brief overview of what I'll be talking about today is basic properties of supersonic pulsars and their supersonic pulsar wind nebulae. The 3 objects of interest today, J1509-5850, not to be confused with B1509-58, which is a different pulsar. There's a poster of it in the poster session if you want to see that one. B0355 plus 54 and J1747 minus 2958, or the mouse. Then I'm going to be talking about compact nebulae morphology and then the connection of that with pulsar geometry and light curves. Misaligned outflows, which are these puzzling structures seen in about 4 supersonic pulsars in recent years. Then spatially resolved spectroscopy of the tails and how we can infer properties of the tail from it, and then a comparison of pulsar tails and the trends we see. So the most important factor in determining a pulsar wind nebula's morphology is the Mach number, which is the ratio of the pulsar's speed relative to the speed of sound in the interstellar medium. Theoretically speaking, if your pulsar has a Mach number lower than 1, you'd get a spherical pulsar wind nebulae, but we don't really see that. We see jets and tori because the wind is mostly anisotropic. If your pulsar has a Mach number greater than 1, you would expect to see termination shock here, which inside the unshocked pulsar wind you wouldn't see any emission, and that's right there in the inner ring of the crab. Outside of the termination shock, the pulsar wind becomes shocked, and you would see synchrotron radiation from radio through gamma. And then the contact discontinuity separates the shocked ISM, interstellar medium, from the pulsar wind and confining it with its pressure. Here's some examples of tails. So supernovas typically give pulsars a birth kick on the order of 400 kilometers per second, although some are as slow as 50 and some are as fast as 1,000 kilometers per second or more. So this means pulsars usually escape their supernova remnant within a few tens of kiloyears. ISM speeds of sound can vary from a few kilometers per second to a few tens, even 100 in some cases. So typically Mach numbers are on the order of 1 to 10, although they can be higher. Supersonic pulsar wind nebulae consequently usually display a bow shock compact nebula, which can take many different forms, and sometimes a long tail, although not all show tails, and sometimes some show a tail without a compact nebula, so that's also another thing. There's about over 230 pulsars now whose proper motions we've measured. There's about 30 fast-moving pulsars who have pulsar wind nebulae seen in X-rays. Fewer are seen in radio, and that's usually because only pulsars with under 1 megayear have enough spin-down energy to produce nebulae. Morphologies are highly varied. We see here that have filled morphologies, some that display the opposite, hollow ones, a combined compact nebula and tail. Some are asymmetrical. Some don't have a compact nebula but have a tail behind it. And then various other less certain morphologies. The first object here is J1509. It's about 3.8 kiloparsecs from its dispersion measure. It's middle-aged and we estimate its velocity to be on the order of 400 kilometers per second. It's seen in radio and gamma rays, and this long 370 ACIS exposure reveals its highly collimated X-ray tail, but it also reveals this long structure ahead of the pulsar's direction of motion. It kind of looks like a headlight. It's one of the examples of a misaligned outflow. And then on the small scale, you can see what looks like two jets, and you can actually, we had 4 separate observations spaced a couple months apart, and you can actually see blobs of plasma moving along the jets at about 0.3 C, which is like similar speed seen in the Krebs blobs along the jets. And here's a radio image. It has a radio tail coincident with the X-ray one, except that there's no radio emission near the pulsar except for the pulsar emission. The radio nebula brightens with distance, and then it fades and narrows. BO355 is a lot closer. It has a parallax distance of 1.04 kiloparsecs and a proper motion of 61 kilometers per second, thus putting its Mach number between 6 and 60. It's a little bit less energetic, and it's not seen by Fermi, and there's no radio tail associated with this. There's been a bunch of searches with the VLA and the JVLA, and nothing was seen, unfortunately. But this deep exposure reveals this very well-defined bullet-shaped or mushroom-shaped compact nebula, which is bright along its central axis. It has this drop in brightness there, and it has about a 2 parsec long tail. It kind of bends slightly here, and then there's hints of a misaligned outflow, which I'll talk about later. And the last one is J1509-5850, the mouse. Its distance isn't very certain, but it's on the order of 5 kiloparsecs. Its proper motion has been measured, and at 5 kiloparsecs, it's 300 kilometers per second. Its spin-down age suggests 25 kiloyears, although it's probably on the order of 50 to 100 kiloyears, since no associated nebula is seen in radio or X-rays. It's also seen in gamma rays as well as in radio. And it features this filled morphology similar to BO355. The X-ray nebula narrows with distance, and then it has this extremely long 17 parsec radio tail that initially widens, but then it kind of narrows. And I think it's one of the longest pulsar tails seen. So the compact nebula morphologies can appear to contrast, but 2 examples of that are Gaminga and BO355. But Gamingo is almost totally radio quiet except for very low frequencies, and it's very loud in gamma rays. BO355 is not seen in gamma rays, but it's very loud in radio. So we can interpret this as that we are seeing Gaminga edge on, and that this is its equatorial outflow crushed by the ram pressure and pushed back, and that these are the jets. Now, if you can imagine, if you looked at Gaminga from above the equatorial outflow, you would see something similar to this. And that's the nebula, and then these 2 things moving away from the pulsar and separating are the jets superimposed on each other in projection. So there's as Oleg said, there's a connection between the pulsar wind morphology and the light curves. The geometry of the compact nebula can be used to obtain your viewing angles. For example, if we assume that this fall in brightness in the mouse compact nebula is similar to that of BO355, we can use a geometry of that to estimate that we're looking at this from above 20 degrees above the equatorial plane. In which case, because we also see the radio pulses, that would give it a similar magnetic offset angle on the order of 70 degrees. We see similar angles for J1509 based on the fact that its light curves in radio and gamma rays are almost identical, not only in morphology, but also in the separation between radio and gamma ray peaks. And that can help us discern less certain pulsar morphologies, like now we know that the mouse is equatorial outflow dominated and that there are no jets, even though we're viewing at it from a similar angle. And also, combining the X-ray images with these light curves can help reduce redundancies in constraints from looking at the gamma ray light curves. Why isn't that? Oh, here we go. Okay. So compact nebulae. The simple isotropic MHD simulations don't always describe what we see here. In the case of BO355, they do, but it doesn't fully capture the anisotropic winds and the misaligned outflows. Also, in many cases, the velocity vector of the pulsar appears perpendicular to the velocity vector, although there are some examples where it's offset or somewhere in between aligned and anti-aligned. And this challenges previous hypotheses of spin velocity alignment, and it can provide clues on pulsar birth kick mechanisms in their progenitor supernovae. So, in recent years, a couple of these puzzling misaligned outflows have been seen. The first one is seen in the guitar, the second one is seen in the Lighthouse Pulsar Wind Nebulae, and then we've found 2 more cases, and then recently a 5th candidate has been found, although we don't really know about its velocity yet, so it's tentative. But at first it was believed that these are the pulsar's jets, but that doesn't really work out that well because pulsars with these kind of speeds, their jets would bend on very small, almost arc-second scales. And also in these 2 pulsars, we can see the jets, so these definitely aren't the jets. So Bandiera, to explain the guitar, suggested that in high Mach pulsars, the bow shock standoff distance becomes smaller than the electron gyro radius of high-energy electrons. So then the high-energy electrons can't be contained within the bow shock and can then leak out into the interstellar medium where they travel along the ambient magnetic field lines. Other theorists have said that for supersonically moving objects, not just pulsars, some galaxy clusters do this, but the ambient magnetic field lines can drape around the bow shock, and the deep images of the Lighthouse Pulsar Wind Nebula kind of confirm that, because you can see this outflow bend, but then bend back as if it's draped around the bow shock. And Bikov et al., to explain the the asymmetry in these, has suggested that the interstellar magnetic field lines can reconnect with magnetic fields in the Pulsar Wind Nebula bow shock or jets, which will allow high-energy particles to be launched along the interstellar magnetic field direction. But because the ISM magnetic fields can only reconnect with the magnetic fields that are oppositely oriented with them, it explains why one side is highly favored than the other. Obtaining the spectra of the BO355 nebula, the compact nebula is hard. Right as you cross over this brightness drop, the spectrum becomes about 1.7, and it stays that up to 2 parsecs down the tail. So that suggests that there's no significant cooling happening along the tail. We model this tail with a simple 1D synchrotron cooling model from Chen et al. It has drawbacks in the sense that it assumes a cylindrical tail and a constant width, flow speed, and magnetic field. But our data suggests either a very fast flow speed on the order of a few tens of thousands of kilometers per second or a very low magnetic field. But the lack of cooling could hint at some kind of particle reacceleration mechanism playing a role here. The J1509 tail, some interesting things happen here. Initially, gamma softens in X-rays moving down the tail. The radio tail expands, as well as the X-ray one, and it increases in brightness. And this is radiopolarimetry showing the magnetic field orientation along the tail. And it's initially perpendicular to the tail axis. But then halfway down the tail, the spectra starts to harden. The magnetic field reorients and becomes parallel to the tail. And the radio tail fades, which is interesting, as well as it narrows. But you would think that if it's narrowing, it should increase in brightness because the particles are being confined to a smaller area. The misaligned outflow cools, which suggests that it's not the same type of outflow as a tail. And the magnetic field also kind of decreases in the second part of the tail somewhat drastically, which suggests that maybe there's some kind of reconnection here. So the Mouse Pulsar Wind Nebula in X-rays is bright enough that we can produce an adaptively binned spectral map of this one. And that allows us to create regions of equal signal-to-noise ratio, which maximizes the spatial resolution for a certain signal-to-noise. And we see here there's rapid synchrotron cooling over a 45 arc-second extent. Gamma almost doubles from about 1.6 to 3 over this extent. However, if we extract the spectra from the entire tail behind the pulsar, it fits a very well constrained single power law model. And that's strange because some of the power laws is not a power law in itself, but here it fits very well. And if we didn't perform spatially resolved spectroscopy, we'd think, oh, that's the spectrum of the tail. But this highlights the danger in obtaining the injection spectrum from large extraction regions and shows that it's best to use a gamma of the uncooled wind near the vicinity of the pulsar. Similar rapid cooling trends are also seen in the Lighthouse Pulsar Wind Nebula. So we plotted the X-ray spectrum here and then the VLA spectrum, and it indicates some kind of spectral turnover around infrared. So we checked the Spitzer MIPS 24 micron data, and we see a point source where the pulsar is. I don't know if you can see it very well in here, but there are other 2 mass sources circled in green, but there is no source anywhere near the pulsar. And it's definitely not thermal emission from the neutron star surface, because that should be orders of magnitude lower for a pulsar at 5 kiloparsecs away. So the flux from this area kind of fits right on the extrapolation from the X-ray spectrum and also from the lower frequency radio spectrum. The low frequency spectrum has a gamma of 1.2 plus or minus 0.1, and the spectral turnover here is about 0.9. But usually in other tails where we see radio emission, the spectral turnover is about 0.5, so that is interesting here. But using both the low frequency and high frequency spectra, we can estimate the magnetic field in the X-ray tail to be on the order of 300 microgauss, which is quite high, and that also, if this is true, suggests a very low flow speed here on the order of 1,000 kilometers per second or less, and that would explain the rapid synchrotron cooling seen here. Also, radiopolarimetry of the mouse suggests that its magnetic field is aligned parallel to the tail, at least in the near vicinity of the pulsar, which is the opposite of what we see in J1509. So, in summary, cooling trends can vary. You can either have no cooling, rapid cooling, or even reheating or reacceleration parsecs away from the pulsar. And this could be because of different magnetic field strengths, changing flow speeds, or magnetic reconnection. The tails can widen with distance, so they can become narrower. They can bend in some cases and dim and brighten. And this can reflect different ISM densities, temperatures, and pressures, or entrainment of ISM matter, like it being pulled into the tail. So that studying these tails allows us to probe the interstellar medium better. Misaligned outflows, they're asymmetric, seen at very different angles with respect to the pulsar velocity vector, and they're likely caused by particle leakage from the apex of the bow shock into the ambient magnetic field. But these structures are rare. Only 4 or 5 of them are seen, and it's not clear why they're so uncommon or far less common than tails are. The magnetic field orientations and structure can vary. They can even switch, and it's not clear how the magnetic field structure in the tail depends on the spin velocity alignment of the pulsar. Looking at this small sample suggests that there isn't a very clear relation on the two. And lastly, X-ray images of pulsar and nebulae can be combined with multi-wavelength timing data to place constraints on the viewing angle and pulsar magnetosphere and geometry. So that's the end of my talk. Thank you. Are there any questions?
Thank you, Noel. Nice talk. You finished it in time, which is also important.
Nice.
Please, questions.